In this question, we're going to do some guided exam question practice on the 2002 exam paper question on first ionization energy trends. Now, from my experience, my students have found certain parts of this question quite difficult, so I'm going to take you through certain areas and what to look for. Okay, so the first thing is it's on first ionization energies, and it was a question 5. It's a full question, so you're talking 20 minutes. So the usual reminder: get yourself out a timer, set it for 20 minutes, and let's get started. Okay, so it says here in the beginning, it says to refer to the data in the maths tables on page 44 to 46. Now you may have your maths tables there. If you do, you can open them up. If not, I have it printed out down here. This is what it should look like. It's a periodic table and it has first ionization energies written at the top. And here is each element and its atomic number at the top. So this is the atomic number, the same as it is on a known periodic table. But on the bottom, instead of the mass number, you have the first ionization energies. So first IE, first ionization energy for each different element. That's the first thing. Right, let's jump into the question. All right, so for 8 marks, okay, so 8 marks, standard definition. This was the first year of this new chemistry paper. Usually definitions are worth 6. In this case, it was worth 8. And we'll jump you through the definition, standard definition that we learned. Okay, so what is it? The definition is, so again, I always advise you to write down over here, what is it that you're talking about? First ionization energy. Definition for this is it's the minimum amount of energy. So that's important. It's the minimum amount of energy required to do what? Dot, dot, dot. So pause the video, finish off the question. You should know that definition, pretty straightforward. Okay, so you're going to be playing if you've finished writing this out. So minimum energy required to do what? The minimum amount of energy required to remove the most loosely bound electron is how you should have phrased this. This is the most loosely held on to electrons, the most loosely bound electron. So the most loosely bound electron, that's what they were given 3 marks for there. From a mole of gaseous atoms in their ground state. Ground state. All right, so that's the full definition there. Okay, and like I said, usually it's what 6 in this year. It was the very first year. It was what 8 this year. Okay, so straightforward definition, not too much to talk about there. If you want to understand what first ionization and energy is about, if you're only seeing this for the first time, then I advise you to go and watch my video on what first ionization energy is. Okay, let's jump back to the previous question. This is one of the places where students went wrong. Okay, so see what it says here. It says account fully. Now, I just want to point something out to you. See this one here, it says account fully. And if we look at part C, it just says account for the trends. This word here is, I don't like the way this is done, but this is the way it was done in this particular question. Account fully. And there was 15 marks here, which means you're looking for a significant amount of information. It's more than this. Look, this was only 6. So account fully, they're looking for something extra. What is it that they're looking for? That's going to be important. So account fully for the trends in first ionization energies of the elements across the second period of the periodic table. Again, 15 marks. Remember how marks are given out in chemistry, usually in 3s. So this is basically 5 3s. Now, let's jump down. Okay, we're talking about the second period, so that's definitely something to point out across the second period. The trends, and we're looking for first ionization energy. These are the elements, lithium to neon. Let's jump down here. Second period is here. N equals to 2. Second period begins with lithium and ends with neon. Okay, so what is happening here? Okay, let's see. What do we see? It starts at 520 and it goes over to 2080. First ionization energy increases from lithium to neon. That's what most people would do. They would see that trend, they would explain it, and they would move on. Let's do that first of all. Okay, so this is is it B or part 2? It's called B. So we'll label it part B. B. And plus N equal to 2. I don't know what's wrong with my OneNote there. So across n equal to 2. First ionization, let's state what happens first. First ionization energy. So I'm just going to pause the video and try and fix this screen because it's playing up. So I'm just going to pause for a second. Apologies about that. So let's state what happens in the n equal to 2 energy level. First ionization energy increases. That's what we saw down in the table. Increases due to. What are the reasons? Right, the first thing that's happening is when we go left to right across the periodic table, the atomic radius is decreasing. So the atoms are getting smaller and the outer electron is getting closer to the nucleus, which is going to make it harder to remove. So due to the, atomic radius is decreasing. And in addition, as we move over, if we go down here and check what else is going on, as we go from lithium to beryllium to boron to carbon, the atomic number is increasing, which means there are more protons in the nucleus. So the nuclear charge is getting bigger, okay, which is going to make it harder to take an electron from it. Okay, so atomic radius is decreasing and the nuclear charge is increasing. Now, most of my students stopped here. Now, what I'm saying to you though is that this is only these, basically each of these is a scoring point. That's 3 and that's 3. So we've only got 6 marks so far out of the 15 that was going for this part B. So what else are they getting at? Well, there's something in this word, this account fully for what's going on. Let's see, is there anything else going on here? So let's go back to our n equal to 2 period. Remember that we would have learned about a general increase, 520 going up to 2081, but that isn't the full story. Okay, the full story means we have to look within the group. Here, from 520 to 899 goes up, but it doesn't keep going up. It drops to boron. So beryllium has a higher than expected value. So 520 goes to 800, but this one seems to be extraordinarily high, more than it should be, okay? Then it's going up, and then there's a big jump up to 1402 before coming back down to oxygen, where that doesn't go down that much. So it goes up, there's a big jump up to nitrogen, down to oxygen, and then continuing up, up, up. So there seems to be a spike there at nitrogen and a spike there at beryllium. This is what they're getting at when they're talking about account fully. And this is very frustrating for my students, because if they were asked about these, I know that they'd be able to explain them. But this question, the way it was worded, didn't specifically ask that they wanted you to explain it, but they expected you to be able to pick out and understand that by saying account fully and giving you 15 marks, whereas this one just is account for 6 marks, that you would know that there's extra needed. Very frustrating in my opinion, but unfortunately that is the way the question was asked. So how can we explain this then? Okay, so first ionization energy increases generally, that's a general increase. So what we're going to talk about next is that beryllium, Be, has a higher than expected, i.e. first ionization energy, due to having a full, and it's a 2s sublevel. Okay, so if we think about beryllium, it's got electronic configuration 1s2, 2s2. That's it. It's got 4 electrons, and this is its configuration. And this here is a full sublevel, which is extra stability. This here gives extra stability, which means that it gives us a higher than expected first ionization energy. So it gives extra stability. So you should definitely be using the word stability in here. The other one then is the other unexpected value maybe is nitrogen. Nitrogen has a higher than expected. So they're just higher than they expected due to in the trend. They're just a little peak in the trend, if you like. Higher than expected ionization energy due 2 having, and what is the reason? Well, if we think about nitrogen's configuration, it's 1s2, nitrogen has 7 electrons. So pause the video and write down the rest of nitrogen's electronic configuration. Do that now. Okay, so it's 1s2, 2s2, that's 4 electrons, and then it's 2p3. This here is half full. It's half full 2p sublevel. This here has some added stability, added or extra stability. That makes it higher than expected. It breaks the general trend. Just go up a little peak in the trend. All right, so that was it. That's what you needed for the 15 marks. Okay, and I know, in a way, I think that's an unfair question. I think they should have separated into 2 parts, asked what the general trend was, and then asked about beryllium and nitrogen. In my opinion, that would have been more fair. But these are the things you need to watch out for. This is to separate really top students from the others, but I still think it's not really fair. All right, in the next question, part C. Account for the trend in first ionization energies of the elements going down the group 2 of the periodic table. So the alkaline earth metals. So group 2. So first of all, you need to know what a group is in this periodic, in a periodic table. A group is a vertical column. So this is group 2 here. Okay. So the trend here, what you're seeing, starts at 899, then 737, then 589, then 549. General trend is it's decreasing. Okay. So we know now it's decreasing. Why does it decrease? So jumping back over here to where we're writing our answers out. Sorry, a bit messy all over the place here. Yeah, so we're in part C here. Part C. So ionization energy down group 2. All right, so what is going on? Explain what happens. So what we say, there is a general decrease. Again, so you put this into a sentence, general decrease. All right, pause the video and explain the reasons why you see a general decrease in first ionization energies. Should be doing that now, please. Pause the video, do that now. Okay, so show me watching the video if you've tried to explain why there's a general decrease in first ionization energies down group 2. Right, the first reason for it is, well, as we move down group 2, we're adding in extra shells. And what that does is 2 things. It increases the atomic radius, which puts the outer electron further away from the nucleus. And if it's further away from the nucleus, it's easier to pull off. What we've also done is by adding inside shells full of electrons, we've increased the screening effect. So there are the 2 things you should have said. We've got increased atomic radius. And we've got an increased screening effect. Well done. If you got those right, that's brilliant. Screening effect. Again, you should know those very well. You should have studied all them patterns very carefully. Right, the next one was where students found another challenge. Okay. It says here the approximate values for the first 8 ionization energies of magnesium. Okay, so something that some students got wrong here is they didn't realize that this was the first 8 ionizations for one element. They were looking at different elements. I don't know, students mix this up. You take magnesium, you take the first electron, that's called the first ionization. Take a second electron, that's the second ionization. Take the third electron, that's the third ionization, and so on. Okay, so it says, so here are the values. As you can see, the general thing that we see is that it takes more and more and more energy every time you try to remove an extra electron. Okay, so here it says, explain the reasons why there is an increase in these ionization energy values. Now, what students start trying to talk about here is, oh, you move across the group, or the screening effects increased, things like this. Unfortunately, this wasn't the case. Let's take a look at what we should have been thinking about here. This is part D. Okay, I'm going to quickly draw a diagram here, and we'll try and explain what happened. Try and explain maybe why it takes more energy. So here, let's say we have an atom. We call it X. Okay, and we remove an electron. So X, take away 1 electron. What does that create? It creates an X plus 1 ion. We've created an X plus 1 ion. So it took a certain amount of energy to remove that electron. Okay. Energy, we put energy in to take that electron away. That's the first ionization. If we try and then take this thing and start again, X plus 1 and try and remove another electron from it, then that would be the second ionization energy, and that would create X2 plus, the 2 plus ion. Now, the question is really asking, why does it take more energy to remove this second electron? And then if we did it again, why would it take more energy to remove the third electron? And what you need to do is think about, what are you removing it from? In this first ionization, you're taking it away from a neutral atom where the number of electrons and protons are the same. In the second example, you're taking it away from a positive ion, which is going to be, it's more positive than this was. Overall, it's got a higher net positive charge. So if it's got... Apologies about that interruption. Intercom in my school went off. Yeah, so where was I? Yeah, removing the second electron in the second ionization is taking the electron away from a positively charged ion. And obviously a positively charged ion means there's more positive charges than there are negative charges. So you're essentially trying to drag the electron away from an atom that has more positive charges than the negative charge. And it's going to become harder and harder the more positive this gets. So what I want you to do now is I want you to put that into an explanation, okay? I'll remind you what the question was again. Explain why you see this general increase in ionization energy values as you take the second, the third, the fourth, and the fifth, and so on. Okay, so put what I've just explained into an explanation. Pause the video and do that now for part B. Okay, all right, so you should only be playing if you've had a go at putting this into an explanation. Okay, increase between ionizations. Why does it get harder each time you ionize something to take the next one? Well, the reason for that is that the electrons are being removed from a more and more positive ion or positive atom. Okay, so the positive charge is increasing. Okay, that's the reason why the more positive it becomes, the more harder it takes to remove another negative charge from it, because it likes to be balanced. It wants to be balanced and even. So taking more and more negative charge away from a more and more positive thing is going to become harder and harder to do. The other reason, and I think that this was again, this is a tricky one. That there was what, 6 marks, guys. So that was 6 out of the 9. There was 9 going for this. The other thing is that when you take an electron away and you get a more positive ion, that makes the atom a little bit smaller because you've got more positive charge in the nucleus for the amount of negative charges you've got from the electrons. So it can suck the electrons in a little bit. That's a really hard idea to grasp and probably a tough one for most students to get these 3 marks. But just in case you ever see it again, once you've removed, or after each ionization, the atom's getting a little bit smaller, a little bit smaller, a little bit smaller, because the more and more positive nucleus, the more positive charge overall is sucking in the electrons a little bit tighter. So that's the second reason, is that each time you remove an electron from an atom, if you remove another one and another one and another one, the atomic radius will be decreasing due to the fact that the nucleus is more and more powerful compared to the electrons. It's pulling them in. Tough one, very tough 3 marks there. Right, next bit. Question 12 marks here. So again, 12 marks usually means 4 times 3. So it says account for the dramatic increase in ionization going from the second to the third ionization. So is there a dramatic increase? Yeah. 1450 to 7750. That's pretty dramatic. That's a pretty big jump. Compared to the other jumps here, that's quite a big jump. It's the first big jump we see. So account for that. Okay. Now, notice though that there is another part to this question. So be careful to come back and read it again. So let's just jump for that. Okay, so this is part E. Part E. And it's account for the jump. Or jump from second to third ionization of magnesium. Okay, so what do we say? Well, if we think about it, if we think about magnesium for a second, it's 1s2, 2s2 is the electronic configuration. Okay, so if we take one electron, then it's 2s1. And if we take the second electron, it's 2s0. This whole thing is gone. So now this is the configuration. So that's after 2 ionizations. And to take the third one, we're taking this one of these to make it 1s1. So why does that give us such a big jump? Okay, so again, what I want you to do is pause the video and account for the jump in second to third ionization. Do that now. Okay, so you should only be watching if you've written down a reason for that. Okay, so the reason why there's such a big jump is because the third electron, as it's been taken, the third electron is taken. There's a couple of ways you could word this, taken from a full main energy level. Actually, this is magnesium, isn't it? I was doing beryllium there. So magnesium, sorry, is 1s2, 2s2, 2p6, 3s2. Sorry, that's I made a bit of a mess of that. So after the first ionization energy is 3s1. After the second ionization energy is 3s0, which means that this is gone. And the third ionization energy is coming from here. So that was my bad. So it's coming from here. So it's a full main energy level. So the second energy level is full when you're taking the third electron. And again, most of my students were able to answer this, so I don't think this is too difficult. Third electron is taken from a full main energy level, or you could say full main. You could even be more specific. N equals to 2 main energy level. I think that's energy level. Another way students say this is that third electron is taken from a full outer shell, which will get you the marks as well. You could say it's taken from a full 2p sublevel, which will get you the marks as well. You could say after the second ionization energy, the atom has a stable octet or a full octet, or it satisfies the octet rule. A few different things you could say, all right? But this is basically the gist. You'll have to read it. It has to mean the same as what this is saying here, basically. Right, so that's C plan. That was what 6 of the 12 marks. That there. Okay. The other 6 then is we need to go back here. Remember, 6 marks. You've got to be careful. If it's 12 marks, there's probably a few bits in here. So there is another bit here. It says between which 2 ionizations would you expect to see the next dramatic increase? Now, there's an important word here, the next dramatic increase. We might see some slightly less dramatic increases somewhere, but the next dramatic increase will be in a very specific place. So the next dramatic increase to occur for the data if further ionization energies of magnesium were examined, and give a reason for your answer. Okay, all right, so let's jump down here. Finish this off. So next dramatic increase and reason. Okay, so pause the video and tell me when the next dramatic increase will be and give me the reason for it. Pause the video, do that now. Okay, there's a couple of answers that they would have accepted here, but there's only one really that I think is the right answer, because they asked for the next dramatic increase. So they're looking for the next one where it's another full main energy level. Okay, so at which stage will magnesium be at a full main energy level? So again, let's go back up here for a second to our periodic table. I'm just going to rub all of this out for a second, all this color, and we'll just get our hands on magnesium. Okay, here's magnesium. When you go first at 1 ionization energy, it's essentially now gone to there. It's got 11 electrons. Then it goes to here, got 10 electrons. So after the third ionization, it's been taken from a full main energy level. It has a configuration like neon after the second one. And after the third one, it's been taken off a neon, if you like to think of it like that. Then we got 4th, 5th, 6th, 7th, 8th, 9th, and the, sorry, I need to count them again. Apologies, I've made a mess of that. Okay, so from here to here is 1, then to 2, then to 3, then to 4, then to 5, then to 6, then to 7, then to 8, then to 9th, and it'll be then when we're taking the 10th electron, it'll be like helium, and taking it from helium would be the one where there's a massive jump. Okay, so that would be on the 10th to the 11th electron. So between the 10th and the 11th electrons, or on the 11th ionization, it would be, we would expect to see the next massive jump. Okay, so it was, I would say here, between the 10th and 11th electron. And the reason for that, what is the reason for that? The reason is, well, again, this electron, or the 11th electron, this time it's been taken from a full n equals to 1 energy level. 11th electron is taken from a full n equals to 1 energy level. Okay, now there's another way you could have done this as well. Some people would have looked for like full sublevels or half full sublevels. Those could have been okay as well. I just don't think that the increase would have been dramatic. So just looking at where else you might have got the marks. So just if we go back up here for a second, we take a look at, where are we? Magnesium. So obviously from the 2nd to the 3rd, that's obviously going to be a pretty big one. Then from the 3rd to the 4th, from the 4th to the 5th, from the 5th to the 6th, from the 6th to the 7th, from the 7th to the 8th. Now that's quite stable when it's like beryllium. So from the 8th to the 9th, you might have said as another one there. So you might have said between the 8th and the 9th, and they were allowing you marks for that, 8th and 9th electron. They were allowing you marks for this if you then gave as the reason for this was electron taken from a full S sublevel. Now, personally, I don't think, you know, they did allow that, but I think that the original answer that we talked about up here is much better. And I hope you can see why, because they're dramatic increases. These would see a little jump, but not as much. Okay, guys, so that is that question. As I said, it was a tricky little one. I'll leave the marking scheme here for you to have a look through for your own understanding there if you want to check anything again. But yeah, tricky little question, especially part B. I would prefer if they broke it down for you a little bit more into different parts, but they didn't, and that's sometimes what you have to deal with. So yeah, that's it. We'll see you in the next question.